Thank you. So the second talk today is by Bharat Adsul. I think it's the first of two talks, so it's a preparatory talk, sorry, for the talk by Milind Soni. And so it will be about affine versus projective orbit closures, Lie algebra actions and constructions. So you can start whenever you're ready.
Yeah. Okay. So yeah, I think I'll just start. Yeah. So first of all, I would like to thank the organizers for giving me this opportunity to talk about this some of this exciting work that I'm doing with Milind Soni and KV Subramaniam. Yeah. So as Thomas just said, this is really a background talk, sort of for the main talk, which will be given by Milind Soni. I think the main talk is on Thursday. Yeah. Okay. So, oops. Yeah. Okay. So let me begin. Okay. So this is the outline of the talk. I will sort of begin by just recalling the basic setup of group actions, and I'll sort of make this distinction between affine and projective orbits and their closures. Okay, then we'll look at these Lie algebra actions. We'll look at some of the key questions that sort of motivated our joint work, and then I'll talk about this Lunar slice theorem and so on and so forth. So let me not spend more time here. Let me just get into the action, the group actions. Okay, so we have this right. So we have this group G. This is a linear algebraic group, and I'm going to stick to complex numbers. So the underlying field is complex numbers, and some of the examples that you should keep in mind are the GLN, so n by n invertible matrices, and SLN, so matrices, invertible matrices with determinant 1. Okay, so so I have this G acting linearly on a vector space. So there is this action map, right? Yeah. So given a group element G and given a vector V, I sort of this group element moves this vector V to this point G dot V, right? And this is a linear. This is linear in V, right? And of course it's an action. So corresponding to a linear action, we also have the representation rho, right, which for every group element associates the corresponding invertible operator on V given by this action. Okay, so here is a simple example. So suppose I look at K star, so which is 1 by 1 invertible matrices, and it acts on this two-dimensional vector space K2 via this representation. Okay, so the group element T is mapped to this 2 by 2 matrix, invertible matrix T00 T. Right, so I have this action of GL1 on this two-dimensional vector space, and therefore I have the associated action on the polynomial functions on this two-dimensional vector space. Okay, so I'll just denote, write these x and y as these coordinate functions on this two-dimensional vector space, and then the action, the GL1 action on V induces this action on this ring, namely the polynomial x is sent to the polynomial Tx by the group element T, and the polynomial y is sent to the element T inverse, to the polynomial T inverse y, right? And as you can clearly see, the polynomial xy is an invariant, and in fact every invariant is in fact a polynomial in this invariant xy. So the ring of invariants is generated by this by this single polynomial xy. Okay, so this is our general setup, right? So I have a representation, and then these are the basic objects of study: the orbits, the stabilizer, and so on. So the orbit of a point P is, just take this point P and translate it by the various group elements and see where all you reach. That's the orbit of the point P. Then the stabilizer of the point P is those group elements which fix the point P, right? And here is a very important notion, namely, a point P is said to be stable if the orbit of this point P is closed in, right? And closure can be talked about in Zariski topology or equivalently equivalent topology. So stable points are the ones whose orbits are closed, right? So if I look at this simple example, two-dimensional example, right, where K star acting on this two-dimensional space via this T inverse map, right? So as we saw, xy is the invariant polynomial, and this, for example, this blue part, right, is a stable orbit, right? It's essentially the hyperbola, and this is a stable orbit. In this picture, you also have this green line, the y-axis, right, minus the origin. So that's a non-stable orbit, and in fact, 0 is in the closure of this orbit, as you can see. Right. Similarly, the x-axis is this red orbit, which is also not closed, and this, yeah. So in fact, in this case, so these are the points on the x-axis and the y-axis can be driven to the point 0. At the orbit, the closures of these, the closure of the green orbit contains the origin. The closure of the red orbit also contains the orbit, contains the origin, and this is the null cone, right? So the null cone is those points whose orbit closure contains the origin 0. Okay, so that is a picture. And so given this group action on V, which is linear, it also naturally induces the action of this group on the associated projective space. So PV is the set of lines in V which pass through the origin. So, and so of course I have an associate, because lines move to lines, I have an associated action of this group G on this projective space. So given a non-zero element of this V, I'm going to denote by the line passing through P by this square, right? So that's the projective point associated to the point P in the vector space, right? So of course one can define the projective orbit, right? So if I look at a projective point, I move this projective point in the projective space by the group elements, and I get its projective orbit. So one way to think of it as a subset of the projective space. Another way to think of it is just think of it as a cone over the affine orbit of some representative on this line. So take a point P, look at its affine orbit, and look at its look at its orbit, and take the cone over that affine orbit. That's another way of thinking about projective orbit. Okay, so one can also talk about the projective stabilizer. So given this projective point, look at all the group elements which fix this projective point, or in other words, we just move points on this line to themselves, right? So of course, in general, the projective stabilizer may be larger than the affine stabilizer, right? And these new elements in this projective stabilizer are essentially going to move the point P to some multiple of P. Right, and one very crucial sort of difference between the affine orbits and projective orbits is that although in some sense most of the affine orbits are closed, right, most of the projective orbits are not closed. Okay, so this projective orbit is almost always non-closed, right? So you can think of non-closed either in the projective space, or you can look at this cone over the affine orbit and think of it, the cone being closed in the affine space. Okay, so even when the point P is stable, the projective orbit need not be closed. Okay, the affine orbit is closed. That's exactly what it means to say that P is stable. Okay, so let's look at this example, this sort of hyperbola example, right? If I look at the projective point, so I can kind of parameterize lines through the origin by these points on the circle, right? So what I have tried to draw on this circle are this projective orbit. So I have this blue affine orbit, right? But if I look at its, if I look at a point here and look at its projective orbit, I'll get this projective orbit, and you see that this projective orbit is not closed. In particular, its closure is going to contain this green point, right, which is the line corresponding to the y-axis, and also, right. So in this example, you see that although the affine orbit is closed, the projective orbit is not closed, and this is sort of typical. Okay. Okay, so now we have seen affine and projective orbits. Let me also introduce these Lie algebra actions and representations, because they'll play an important role in what I'm going to say next. Okay, so this group action induces a natural Lie algebra action. Okay, and the way to sort of think of a Lie algebra action is just, it's an infinitesimal version of the group action, right? So given a small group element, right, you would like to, and given a point, you would like to say, when I hit this group element to this point, where would the point move? Okay, that's more, just a minute, there's a call, I'll just I think the stop. Okay. Okay. So there is also more sort of more abstract algebraic viewpoint. In this viewpoint, so you have this group G, and you look at the tangent space to the group at the identity element. That's a vector space. That's the tangent space, and that I am denoting by this calligraphic G. Okay, so this thanks to the multiplication of the group, this vector space calligraphic G, the Lie algebra, has a Lie bracket operation on it. So there is a bilinear operation which satisfies this Jacobi identity. Yeah, but let's look at it in a very particular setting. Okay, so if I, for instance, look at the group of all invertible linear maps from V to V, this is the group, the GLV. And if I look at if I look at the corresponding, the tangent space to GLV at the identity matrix, I will get the set of all linear transformations on it. Okay, so that I'm going to denote by small GLV or just endomorphisms of V. So this is the Lie algebra corresponding to this group, and the Lie bracket operation here is just the commutator on matrices. So given two matrices X and Y, two operators, linear operators on V, I just do this XY minus Y. Okay, so that is the Lie bracket operation, and it has this, it satisfies the Jacobi identity. Okay, and given a linear action of G on a vector space V, so given this representation rho, I can sort of differentiate this representation at the identity element, and I get a Lie algebra representation, right? So I get so this derivative of this rho at the identity element is a map from the tangent space to the group at tangent space to G at E to the tangent space to GLV at E, and so I get a map, linear map, right, from the Lie algebra of G to Lie algebra of GLV, right? And, okay. So for the purpose of this talk, I think it will be better to have a more geometric view of the Lie algebra action. Okay, so suppose I have this Lie algebra representation, right? So it's a sort of Lie bracket preserving map from G to and V, and then I can look at the associated Lie algebra action. So given this infinitesimal group element, that's how I would like to view Lie algebra elements as, and a vector, right? I kind of apply rho prime of that infinitesimal group element is a transformation on V. I apply that transformation to a particular element of V and produce another element. So this is what I mean by this at action, right? So it's just coming from this rho prime. Okay, and yeah, so here is the sort of a more geometric picture of this Lie algebra action. So for a point P in this vector space V, and for an infinitesimal group element G or a Lie algebra element G, this action G at P essentially tells you if I move the point P infinitesimally by this infinitesimal element G, in which direction the point P will. So this is just the direction along which the group element moves the point. Okay, so and this operation is bilinear. Yeah, so this linear in both the Lie algebra element as well as the point under this point. Okay, so yeah, so you should really think of is that once I fix a infinitesimal group element, right, it produces a vector field on the vector space, right? So for every element, if I move this element, it will move in a certain direction, right? And this happens for every element, right? So every Lie algebra element produces a smooth vector field on V, right? So this is yeah, so this is when you have a linear action of the group. This is how the induced Lie algebra action can be thought of. But if you have a non-linear action, so suppose I have a group G and it is acting on this M, which is a manifold or variety, right? So suppose I have a group action, then given a Lie algebra element G, right, it kind of produces this smooth vector field. So I'm going to denote it by XG, right? So let this Lie algebra G goes to the vector field XG on the manifold M. Right, and if you look at the set of all smooth vector fields on M, I'm going to denote that by vec of M. That's also, there is a Lie algebra, canonical Lie algebra structure on this space, which is coming from the Lie bracket operation of vector space. Okay, so if I have a group action, then it naturally induces this Lie algebra homomorphism, which for every Lie algebra element, maps, every Lie algebra element is mapped to the corresponding smooth vector field that it generates on it. Okay, and then this association is kind of bracket preserving, right? So there is a bracket operation on G, and there is a bracket operation on vector fields, and this association of mapping a Lie algebra element to the corresponding vector fields is Lie bracket preserving. Okay, so this is how you think of nonlinear action. But let's sort of look at some concrete examples to see that, in fact, the Lie algebra actions are much easier to deal with. Okay, so if I look at this hyperbola example, this is the group action, right? Rho of t goes to this sort of invertible matrix. So if I take the derivative of this with, at the one element, which is the identity of k star, I will get this map, this linear map from k to the 2 by 2 matrices, to the linear space of 2 by 2 matrices, and the element 1 will get mapped to 1, 0, 0 minus. Right. So if I look at this Lie algebra representation, right, and if I look at a point alpha beta, right, in this two-dimensional space, and apply this linear operator on that vector alpha beta, I'm going to produce the vector alpha minus beta. Okay, so essentially what this is saying is that the infinitesimal movement of alpha beta is going to be in the direction alpha minus beta. Okay, so I kind of produce this vector field everywhere, right? And you integrate this vector field, and then you get the orbit. In this case, it's a one-dimensional sort of action. The group is one dimensional, so just by integrating this vector field, you get the orbits. Okay, so that's yeah. So this vector field view is quite useful. Okay, let's look at some more examples of Lie algebra action. So let's look at the GLN action on the space of degree d forms in n variables. Okay, so I have this n variables, say little x1, little x2, all the way to little xn, right? And I'm looking at the vector space of homogeneous polynomials of degree d in these n variables. So that's this space, that's the space sim dx, right? And we have the action of the GLN, which is just to sort of you take this matrix G, right? Suppose it's given by this data aij, right? You just substitute these variables x1 to xn by the linear transformation kind of defined by the matrix, right? So you look at this this vector variable x1 to xn, right? Multiplied by the matrix A, you will get a sort of a column of these linear expressions in x1 to xn, right? And you substitute each xi by the corresponding linear expression, right? So this is just the standard action on forms, right? So let's see what the Lie algebra version or the induced Lie algebra action is in this case. So in this case, I need to pick a Lie algebra element. So I have called it by this matrix Bij. So this is just an arbitrary n by n matrix, right? And the way this Lie algebra element acts on F, right? So that the G acting on F is going to push it in this direction. Okay, and the direction is that you essentially do this computation. You look at this, you look at this sum where you differentiate F with respect to xj, multiply by xi, and then multiply this by this coefficient Bij, right? And take the sum over i's and j. Let's look at one example here. So I have this G, which is given by this matrix 1, 1, 1, 0, and the form F is this degree 2 form in two variables x square plus x, right? So if I hit G, if I look at this Lie algebra element G acting at this polynomial F, right, I'm going to produce this element. So this is just yeah. So because of this one, I have this one, I multiply by x and take the partial derivative of f with respect to x, and this one corresponds to this term. This one corresponds to this term where I differentiate f with respect to y and then multiply by x, and this one gives rise to this term where I differentiate with respect to x and multiply by y. Right, and this being 0, of course I don't have the term where I differentiate by y and then multiply by y. So if you do this computation, you'll see that this is what we get. Okay, so it's very easy to do this Lie algebra action. Okay, it's much easier than this substitution, right? You can see, and that's kind of expected because the Lie algebra action is supposed to linearize the non-linear group action. Okay, so let's look at another example, namely the conjugation action. Okay, so I have the group is invertible m by m matrices, and the vector space is the space of all m by m matrices. right? And then so that is my V. So V is the space of all m by n matrices, and the group action is, so given a group element G and given a matrix X, you just conjugate X by the group element G, right? So G, yeah, maps the element point X to the point GXG. Okay, so this is a linear action. And yeah, if I look at the induced Lie algebra action, then it will correspond to this this bracket commutator operation. Okay, so if I look at a Lie algebra element G and look at a point X, okay, so the G acting at X, okay, is going to be this Gx minus X. Okay, that's what happens when you sort of differentiate this conjugation action. Okay, that's the derivative. Okay, so you know, if for instance, if I look at this group element, this Lie algebra element, sorry, this calligraphic G, this group Lie algebra element, and this is the point under consideration. Then when I do the Lie algebra action, I have to compute the commutator of these two matrices. So that's what I've done here. I just computed kind of, and then you see that this is what you get. Okay, so the Lie algebra actions kind of are sort of much more easy for the purpose of calculations. Okay. Okay, so let me sort of just review what what we have seen about this Lie algebra action. So as we saw, in general, the group action induces the Lie algebra action, and yeah, so there is in some sense a dictionary between the group actions and the Lie algebra actions. Okay, and under this dictionary, so if I look at a point P, right, and look at sort of when I look at this Lie algebra action at P, right, I'll produce various vectors, which are associated at point, right? And these vectors will essentially span, right, the tangent space. It will be they will exhaust the tangent space to the orbit, to the group orbit at the point. Okay, so this Lie algebra action at P essentially produces the tangent space to the group orbit at P. Okay, so if I look at this, so there is also a notion of a stabilizer Lie subalgebra. So given this, so given this point P, you look at all those Lie algebra elements which kill P, right? So which act by the zero vector field, which produce zero vector field at P. Look at all those Lie algebra elements whose vector field produced at P is zero. Okay, so that is really the Lie algebra sort of, it's a, so this is a Lie subalgebra of the full Lie algebra. And it is in fact the Lie algebra associated to the stabilizer subgroup. Okay, so the stabilizer subgroup, is also a sort of a linear algebraic group. It's a closed subgroup, and then there is this is the Lie algebra associated to that. Okay, yeah. So so as I said, if I look at this, KP, if there are any questions, please do stop me and.
Sure.
Yeah. Okay. So, this action map at a fixed point P essentially gives you this linear map from the Lie algebra to the vector space, whose sort of kernel corresponds to the stabilizer and whose image corresponds to the orbit. Okay, so that's kind of that's what happens. Okay, so as I said, this is sort of the dictionary to go between this, or to think the connection between group actions and the induced Lie algebra actions. So the group actions are kind of global because they really move the point far away, while the Lie algebra action is just an infinitesimal version of the group action. So they just produce the vectors, which direction, along which directions the movement will happen is what the Lie algebra action depicts. Okay, so they are kind of local, and therefore one can kind of restrict to some some subset or some neighborhood, and then restrict the Lie algebra to that subset, because Lie algebra action is only producing vectors at these points on this subset. Okay, and as we saw, the analog of orbit in the group action is essentially the tangent space to the orbit in the Lie algebra world, right? And the analog of the stabilizer subgroup is the stabilizer Lie subalgebra. It turns out that the stabilizer Lie subalgebra essentially recovers the stabilizer subgroup up to its connected component. Okay, so the discrete information is kind of lost, right? But the connected part of the identity element of the stabilizer subgroup can be fully recovered by the stabilizer Lie subalgebra. Okay, so yeah. Okay, so this is right. So we have seen the sort of this Lie algebra basics. Okay, so let me now say a few words about few words about the work that Minlinson is going to talk about on Thursday. Right. So the central question that that has been sort of the focus is the question about orbit closures. Right. So I have a group G acting on a vector space V. That's kind of fixed. Right. And given these 2 points P and Q in this vector space V, what one would like to know, for instance, is whether the point P is in the closure of the affine orbit of the point. Okay, so you take the point Q, look at its affine orbit, and take its closure. Okay, and you would like to know whether P is in the affine orbit closure of the point Q. Right, so this is what I call affine orbit closure membership question. And of course, one has one has its analog in the projective sense. Right, so you take these P and Q, look at the corresponding projective points at the square P and square Q. Right, and look at the projective orbit and look at the closure of the projective orbit. Right, so sort of analog of this question for the projective orbit question. Okay, so these questions are sort of are very central in algebraic complexity theory as well as in the GCT setting. Right, so for instance, sort of the determinant versus permanent question, right, is essentially a projective orbit, or the GCT version of it reduces it to a projective orbit closure question, right, where Q is really the determinant and P is the padded permanent, and you want to know for what sizes of this determinant and permanent the the projective orbit closure of the determinant contains this padded permanent, right, and that will imply sort of that you can sort of compute these padded permanents by a small formula and so, right. So so there is a lot of sort of interest in these orbit closure questions. Let me also say a few words about the kind of P and Q that one is interested in. So from the point of view of GCT, the P and Qs, like such as this determinant and permanent, are very special in the sense that they are completely determined by their stabilizers, right? So these points can be more or less recovered up to multiple just by knowing their stabilizers. Okay, so they're very special in that sense, right? And in fact, if I look at the determinant point, right, and so the determinant point is of course this the determinant function on this n square variable, and then I have this the GLN square action on these, right, on these forms of degree n in n square variable. So the standard form space action, right? So if I look at the SL action, right, if I look at the GL action, then of course the determinant orbit is not closed because 0 is in the closure. But if I look at the SL action, then the SL action, the SL orbit of the determinant function is in fact closed. Okay, that's one of the results which is proved, which is there in GCT, right? So what we are saying is that, and the GL orbit or the projective orbit closure of the GL orbit is essentially a cone over this SL orbit. Okay, so in some sense, so this question is these kind of orbit closure questions are very central in algebraic complexity theory as well as GCT. Okay, so right, so these questions, because these are questions about closure, essentially they give rise to these what are called here neighborhood questions. Okay, so given a point P, you would like to know which orbits come arbitrarily close to the point, right? Because then you have a way to say, which orbits are likely to close on to the point P or the orbit of P, right? So this is certainly very important, right? So what sort of orbits are present in the vicinity of the point P? The other question, which you would like to, given this, given the special P's and Q's that arise in algebraic complexity theory and GCT, you would like to know how are stabilizers of points in the neighborhood of P related to the stabilizer of P, right? So if I have a point, if I point P, and if I have some point which is nearby P, can I conclude something about the stabilizer of this point near P? Okay, so so these questions have sort of been addressed somewhat satisfactorily, I would say, when the point P is stable. Okay, so when the point P is stable, we kind of understand what kind of orbits close onto the orbit of P. We also understand what what kind of neighborhoods, we kind of understand the action of the group in the neighborhood of this orbit of P, provided P is stable, right? So and recall that P is stable means that the orbit of P is closed. Okay, so one very important consequence of the fact that P is stable is that its stabilizer is reductive, right? Which means that every finite dimensional representation of this GP can be broken into a direct sum of irreducible. Okay, so essentially every invariant subspace has an invariant complement. Okay, that's really that's what we that's an important consequence of this reductivity. Okay, so let me just mention these two pieces of work. One is due to Kempf and of several others. Okay, so this says that if P is stable, so this is important. This is that if P is stable and if there is a point Q, right, whose affine orbit closure contains P, okay, then there is in fact an optimal one parameter subgroup, okay, which drives the point Q into the orbit of P. Okay, so there is this, there is a sort of specific optimization problem that is set up, and then it turns out that there is a unique sort of optimal one PS which drives Q into the orbit of P, when P is stable. And in fact, this optimal one parameter subgroup kind of also aligns the stabilizer of Q, along the stabilizer of P. Okay, so note that because P is in the orbit closure of Q, the orbit of Q is of larger dimension, and therefore the stabilizer of Q is of the smaller dimension, right? While the orbit of P is smaller in dimension, and its stabilizer is larger in dimension, right? Because the dimension of the stabilizer plus the dimension of the orbit is the dimension of the ambient space, right? So essentially, when Q closes onto P, right, certainly the dimension of Q, the stabilizer of Q, is smaller than the dimension of the stabilizer of P. But what the optimal one PS due to Kempf does is that it kind of aligns that if you conjugate, an appropriate conjugate of Q, along this lambda will sit inside. So essentially, there is an alignment of stabilizers, right, that happens through the optimal one parameter subgroup due to Kempf. Okay, so another very sort of important result is this Lunar's slice theorem, and I'll say a little more about that shortly. Okay, so Lunar's slice theorem is about a neighborhood of the entire orbit. Okay, so Lunar's slice theorem describes a tubular neighborhood of the entire orbit OP when P is stable. So this orbit is closed, right? And as a consequence of this slice theorem is that whenever Q is in this neighborhood, right, a conjugate of the stabilizer of Q is in fact a subgroup of the stabilizer of P. Okay, so something similar to what happens in Kempf, but it happens now in the entire neighborhood of the orbit of P. Okay, so when P is stable. Okay, so so let me just spend some time talking about this Lunar model. It's actually quite sort of quite nice, and it's not. Yeah. Okay. So as I said, we are going to work with a point P which is stable, which means that the orbit is closed and the stabilizer is reductive. Okay, so I have the reductive stabilizer and the orbit is closed. Okay, and then you do the following. So I have this point P, right, and I have this orbit of the point, which is a closed orbit, and the stabilizer is reductive. So I can look at the tangent space, right, at the point P in the ambient vector space, which is just V, and then of course the orbit is stable, right? The tangent space to the orbit is a subspace which is stable for the stabilizer, right? And therefore I can ask for a normal slice, which is a H invariant complement to the tangent space, right? And this is really important. The fact that H is reductive, right, ensures that such a normal slice which is stable for H action exists, right? So the reductivity ensures that there is actually a normal size to the slice, which is also H stable, right? So the H action restricts to that slice N. Okay. And now, so this is what I'm really going to use, right? So I have this H action on the normal slice N. Okay. And then essentially using this data, right, we'll construct so-called, an abstract Lunar model. Okay. So this is how it goes. So you look at the action of H on this product set. So G cross N. So I have this group and I have this normal slice. and I move by G like this, right? So H acting on this G comma N is you act by H, you multiply G by H inverse on the right, and you multiply by, H, you multiply H on the left to N. So G dot H dot Gn goes to GH inverse comma H. Okay, so this is an action. This is how G acts on, right? And then yeah, so it's a standard sort of result that in this case the sort of geometric H quotient exists. It's actually a nice object. Okay, and this is what I'm going to call by GXHL. Okay, so you should really think of it as the following. If I look at this group G, the H is going to move. Yeah, so essentially the H is going to move to a coset of H. Okay, so yeah, so I have this. Okay, and I'm going to denote the H orbit, right? So in this quotient space, the points of this quotient space are the orbits, H orbits, right? Because it's an H quotient. Okay, so I'm going to denote the H orbit of G of N, the corresponding point in the quotient, by this equivalence class of the H orbit of G. Okay, this is the notation that I'm going to use. Yeah. Okay, so one way to sort of imagine this this object, this associated sort of bundle over so-called vector bundle over G mod H is this. So this is really the normal bundle of the orbit, right? So you have this point P, right? You have the normal space which is an H, which is kind of which has an H action. So you take that normal space, and then this construction in some sense just twists it around the orbit. Okay, so because the point has stabilizer H, the orbit of this point is nothing but G mod H, right? So because the point has stabilizer H, the orbit is G mod H. You take the slice, this normal slice at the point P, and you kind of just move it around, sweep it around, right, appropriately by this action. And then that's exactly what this object is. Okay, so this is the normal bundle of the orbit, in D. Okay, so and this is exactly what is going to. So so it's kind of remarkable that this object is just purely synthetic and it's just determined by the H action on N, right? So H is acting on N, and that is all the data that I need to construct this H quotient. Okay, so this is going to be the Lunar model, in the sense this is going to be the underlying space of the Lunar model. Okay, so but I also need sort of the group action preserving. So I also need an action on this normal bundle, on this GXHL. Okay, so that's what I'll define next. Okay, so if I look at the group G, it acts on this G cross N just by multiplying the left component by G. So G prime acts on G comma N by just multiplying G by G prime on the left. Okay, so it's an action only on the first component. Okay, because because see, N may not have a G action, right? I mean, N only has an H action. Okay, so G prime acts just by acting on the first component, and you can check that this action of capital G on G cross N commutes with the earlier action of H on G cross. Okay, so because of this commuting, these two commuting actions, when I look at the H quotient of this space, right? So there is a G action, there is also H action. When I look at the H quotient, the G action survives on the H quotient. Okay, and then it's just given by this, right? So if I look at this H quotient, this associated bundle, this associated construction, then the G prime moves this equivalence class to this equivalence class, right? You just So in some sense, the G prime action, G action on this associated construction is also sort of synthetic, right? And we have an explicit description of the G action here. Okay, and as I said, all the data that we are using is the H action on it. Okay. Okay, so this is what. So I just I'm just reviewing some things that we have done here. So we have these commuting actions of H and G. We have the H quotient, and then we have the G action on the quotient. Okay, so we have the model, which is this. We also have a G structure on the model. We also are saying how GI will act on this model. And let's now sort of sort of embed this sort of synthetic abstract model into the ambient space, ambient vector space. So this is done by the map mu. Okay, so right now I'm defining it from the full G cross N. Okay, so the mu from G cross N to V is defined like this. So mu acting on G comma n is, you look at G. So essentially this is the point P, right? This is a vector n in the normal space. I just go to P plus n and I move that element by this group, right? So I move this point P plus n by the group element G. Okay, so it's one of the most sort of natural action that one can think of. Okay, so essentially this is the slice, this is the point P. Right, I take a n, right? I go along n from P and then I hit that with G. Okay, so and one can check that this is a G equivariant action. Okay, as I said, there is a G action on G cross n, right? And so this action is G equivariant and it is constant on H orbit. Okay, so that's a simple calculation. Let's do that. So if I look at this point G comma n and hit it by H, I'm going to go to the point GH inverse comma H. Right. So let's apply the mu, this mu map to the point GH inverse comma HN. So by this sort of, by the very definition, it will go to GH inverse applied to the point P plus H dot, right? And because of the linearity, I can make it GH inverse P plus GH inverse HN. Yeah, I should have written that. So H inverse cancels with this H in some sense, but because H fixes P, right? H is part of the stabilizer of P. H inverse dot P is just P, right? And then I can pull G out again. And therefore, what I'm saying is that this map mu is constant on H orbits, right? So when I move by H, right, and therefore this map mu is going to give rise to a G equivariant map from this Lunar model. Okay, so this is the associated construction, right? And I'm going to get a map from Lunar model, right? And as we saw, we should really think of this as the normal space over the orbit, right? So orbit has some dimension, the normal space has some dimension. And if I add the dimensions, I of course get the dimension of the ambient space, right? So this is sort of a map between, objects of the same dimensions. It's kind of, and then given all the G equivalents and so on, it's not surprising that this map is kind of a local diffeomorphism. Okay, that's exactly the content of Lunar slice theorem in some sense. Okay, so what we have is that this map phi, okay, is going to set up a G isomorphism between an invariant neighborhood of G mod H, which is kind of sitting inside this associated construction, right, as the, and the orbit of the point. Okay, so this is a sort of very, very useful model, Lunar model. And then, as I said, one of the important consequences of the Lunar model is that every point, in a small neighborhood of the orbit of P is going to have stabilizer, which is up to conjugation contained in the stabilizer of P. Okay, that's a very sort of important consequence. Okay, so let's sort of review what we have. So we have this Lunar slice theorem, and so if I have this closed orbit, then there is this kind of neighborhood, right? And so Lunar slice theorem provides a tubular neighborhood of the entire orbit. That's one important thing, right? And there is a description of the G action in this neighborhood, right, which can be factored via an explicit G action on the associated construction, right? So it's really the, right? So we saw that, so there is this isomorphism between the neighborhood of G mod H here and the neighborhood of the orbit in the vector space, right? So this action in the neighborhood of, in the ambient space V, in the neighborhood of the orbit of P, can be understood by just via this action, right? And but one sort of major limitation of this theorem is that it is applicable to only stable points, right? So, and the points of interest in algebraic complexity theory as well as GCT are kind of non-stable points in the null code. Okay, so what sort of what we have attempted to do is to develop a Lunar type, this factorizable model, but which will work for a neighborhood of any P. Okay, so I'll say a little more about what we get. Okay, and one sort of central difficulty in in getting such a factorizable model is that because now this P is arbitrary, right? I no longer have this this thing with me that the stabilizer of the point P is reductive, right? And therefore, right, so the stabilizer, when I have this point P, I have the orbit, right? But I may not have a normal slice, which is also stable for H, right? And that was really the starting point for the synthetic construction of that associated bundle, right, in Lunar's theorem. So the starting point very crucially used the fact that this stabilizer is reductive, and which was a consequence of the fact that the point is stable, right? But all that is no longer there, so one has to sort of take a slightly different route. Okay. Okay, so let me just say what we kind of what we managed to achieve is that we develop a Lunar type model which applies to all points. Okay, so but unlike Lunar model, which is a model for the neighborhood of the entire orbit, our model is local. Okay, so we restrict to a neighborhood of the point. Okay, so given a point, I'll carve out an appropriate small neighborhood of this point, right? And this model will kind of talk about the G action in that neighborhood. Okay, and the fact that I'm kind of localizing my attention to the neighborhood of this point means that I need to now work with the Lie algebra action, right? Because the group action doesn't even is kind of is meaningless now, because I sort of decided to restrict to a neighborhood of this point, right? Because the group elements may take you out of this neighborhood. Okay, but the Lie algebra action still makes sense, right? And therefore, what we have is a Lie algebraic local model for a neighborhood of an arbitrary point. Okay, and yeah, so just like in Lunar's case, right, we have this sort of we sort of have an explicit action on this associated construction in the Lunar case. We also have an explicit description of the Lie algebra action on the model. So the model is kind of factorizable. There is sort of a orbit component and normal component, right? Where normal is not necessarily stable under the stabilizer, right? That was the main difficulty, right? But we still have this product form, and then there is of course a shear effect and so on. But we do have an explicit description. Okay, so one important application of this this local model was to understand this projective orbit closure question for the conjugation. Okay, so we apply the local model to the conjugation action and understand orbits in the vicinity of nilpotent, in the vicinity of nilpotent points. Okay, so understand geometry in the vicinity of nilpotent points. So if I look at the nilpotent points are of course far from stable, right? They are in fact the ones which can be driven to they're in the null cone, so they can be driven to zero. So zero is in the orbit closure, right? So we can actually this local model is applicable to points in the null cone, and it actually allows us to recover the some information about projective orbit closure. Okay, so what I plan to do next is that I want to actually talk for next 5-10 minutes. I don't know how am I doing in terms of time, not too good, I guess. Okay, so I want to so KV, what is the you are not audible, I think. You're muted.
So you have 10 minutes still.
Oh, okay. Okay, so this is what I do. Okay, so I look at this conjugation action, right? So I already talked about this, right? So yeah, and in this for the conjugation action, of course, the two matrices are in the same orbit if and only if they sort of represent this. They are similar, right? So orbits are parameterized by Jordan canonical forms. That's the parameterization of orbits, and of course the invariants are kind of the symmetric functions of the eigenvalues. Okay, and in this case, the stable points for this action, okay, which correspond to affine closed orbits, are nothing but the matrices which can be diagonalized. Okay, so this is a sort of classical fact. Okay, I'm sort of so right. So the key sort of point is that the closed orbits in the in the affine sense, affine closed orbits are parameterized by this numerical data, which is the eigenvalues along with their multiplicities, because the diagonal matrix is essentially given by this data. Okay, so those are the closed orbits. The closed orbits for the conjugation action are diagonal as well matrices, which are kind of parameterized by this numerical data. Okay, so this is Okay, so let's try to understand what happens for the conjugation action inside the null cone. Okay, so if I look at the null cone are the matrices where 0 is the only eigenvalue. So these are the nilpotent matrices. Okay, and then of course, they can also be put into a Jordan canonical form. Yeah, so let me just describe that. So by JA, I will denote this single Jordan A by A block where all the diagonal entries are 0. Okay, so this is a nilpotent matrix, right, of order A instances, an A by A matrix, right? And now the Jordan canonical form will tell us that any nilpotent matrix can be sort of written into this block. It can be written as a as a sort of blocks of these these sort of nilpotent Jordan blocks, right, of sizes A1, A2, and so on, right? And I can I can also reorder them without changing the orbit, so that their sizes kind of are decreasing. Okay, so I do that. So essentially, given a m by m nilpotent matrix, I'm saying it can be brought into this canonical form, right, where it's a it's a block diagonal matrix, where the diagonal blocks are these nilpotent Jordan blocks of sizes A1, A2, AS, where these are decreasing numbers, and of course A1 to AS add up to the ambient size m, right? So these are just partitions of M. Okay, so this orbits in the null cone, okay, and they the orbits in the null cone are parameterized by these combinatorial data, which is partitions of the integer m, which essentially records the size of this nilpotent. Okay, so inside the null cone, we have orbits sort of parameterized by this combinatorial information. And in some sense, if you like, outside the null cone, we have this closed orbits, which correspond to diagnosable matrices, which are parameterized by this numerical information about what eigenvalues and with what multiplicity. Okay, so they're kind of different kinds of data. Okay, so if you look at the orbit closure in the null cone, this is what we have. That given a nilpotent matrix with signature A bar, so A bar is a partition of M, and given another with signature B bar, okay, this A bar, J A bar is in the affine orbit closure of J B bar. If I now leave the partition B bar dominates the partition A bar, okay, where we have this dominant sort of dominance order. It says that if I look at for any k, the first k parts of B add up to more than or equal to the first k parts of. Okay, this happens for every k. So this is the dominance order, and so the dominance order essentially dictates what the affine orbit closures are inside the null, right? Because we're talking only about orbits in the null. Okay, so in particular, if I look at this m by m full one Jordan block with all ones, super diagonal ones, then that is its closure is the entire null. Okay, and it turns out that these if I look at these orbits in the null cone, their orbit closures are in fact are also projective orbit closures. Okay, there are already closed cones. So so inside the null cone, the orbit closures kind of coincide with the projective orbit closures coincide with affine orbit closures. Okay, okay, and you can essentially take this picture inside the null cone and lift it to outside the null cones as far as affine orbit closures are concerned. Okay, but what we want to look at is the projective orbit closure. Okay, so let's look at this point y, this matrix y 0 1 1 0, and let's look at this one parameter subgroup lambda t, which is t 0 0 t. Okay, and let's conjugate this y by lambda t. Okay, so let's look at the action of this one parameter subgroup on this point y. So if I look at this lambda t y lambda t inverse, right? If I do this computation, I get something like this. Okay, and this is t raised to minus 2 and this matrix plus t squared times this matrix. Okay, so if I look at the sort of t to the minus 2, so the least power of t present is t to the minus 2. So if I pull it out, I will essentially get this. Okay, 0 0 1 0 plus blah blah blah, right? And this this point, so I am calling this matrix n here, n plus t to the 4n prime with some negative power of t. Okay, but if I'm looking at the projective closure, this point, right, this point is on the same line as this point, n plus t to the 4n prime, right? So when I look at the projective closure, right, if I look at the projective orbit of y, right, of the line corresponding to y, then it's going to essentially contain these points, right? And now if I substitute t equal to 0, I'll get n, right? So if you look at n, this n is a nilpotent, this n here is a nilpotent matrix. Okay, this is a nilpotent matrix. So what I'm trying to show is that this point y is a stable point. You can it's a diagonalizable matrix, right? But this stable point, the projective orbit closure of this stable point enters the null cone, right? And it picks up this particular nilpotent matrix. Okay, so as we have seen, the projective orbit closures enter the null cone and pick up, and that's what happens even in this case. So this is what we would like to, this is the question that we would like to answer, right? That given an nilpotent matrix X, which can be given by this combinatorial data, and given another matrix Y, which can be described by the Jordan canonical form, right? When is it that this, the projective orbit closure of Y contains X? Okay, this is what we would like to understand, right? So yeah, if I give this is what we want to understand, and we kind of we apply this local model, right, for this top, the top nilpotent matrix JM, right? And by a careful study of this action, we could see a pattern as to what kind of orbits in the projective closure come close to the JM. Okay, and then that sort of led to this this result. Okay, so let me just explain this result. So given an arbitrary, given a matrix Y, which is in this Jordan canonical form, this is what I do. Okay, so I will just so this is a Jordan canonical form. So in this case, you see that there are two eigenvalues. One is -1 and the other eigenvalue is 3. That if you look at the part corresponding to the -1, eigenvalue -1, there are these Jordan blocks. There is one Jordan block of size 2, there is one Jordan block of size 1, and there is another Jordan block of size 1. So if I look at eigenvalue -1, right, and the blocks corresponding to eigenvalue -1, there is a block of size 2, there is one of size 1, and there is another one of size 1. Okay, so I write down this block partition corresponding to this eigenvalue -1. So this is the largest block being of size 2, the next largest of size 1, and the next largest of size 1. Okay, so this is what the block partition corresponding to eigenvalue -1 is. I look at the eigenvalue 3 and look at, there's only one block, Jordan block in this, right, of corresponding to eigenvalue 3, and it is of size 2. Okay, so the block partition for eigenvalue 3 is this 2, and then I just add them component wise. So 2, 1, 1 plus 2, so 2 plus 2 is 4. And then I associate a spectrum block partition to an arbitrary matrix Y. Okay, so in this case, it will be 4, 1, 1. Okay, so this is again a partition of M. Okay, and so this is a combinatorial data that we are associating to this, this matrix Y, right? Which is of course a reading of some, Jordan block information corresponding to different eigenvalues. Okay, and it turns out that this combinatorial data essentially determines which nilpotent orbits are going to enter into the projective orbit closure of this point. Okay, so this is exactly the main theorem. So if I have a nilpotent matrix X, okay, whose signature, that block, nilpotent block partition is theta, and if I have an arbitrary matrix Y whose spectrum block partition is lambda, then the projective orbit closure of Y contains X if and only if lambda dominates theta. Okay, so in the projective orbit closure, in some sense, we kind of lose this very fine information about the numerical information about the eigenvalues. But what is sort of remembered is these block sizes, right? And of course, categorize them by different eigenvalues. Okay, so that sort of information is what is, what is really, what determines the projective orbit closure. Okay, so I will not get into the proof of this, but here is an example of that. Maybe in the interest of time, I'll just skip that as well. Can I go on for like next 10 minutes? I'll quickly. Okay. So this is just an illustration of that result. Okay. So I just want to say, I just want to give a brief introduction to this local model. That really led us to this result about projective orbit closures for the conjugation action. Okay. So recall that this is what we set our objective as. So what we would like to do is we would like to build a Lunar style model of a neighborhood of an arbitrary point P. Okay, so let's look at the stabilizer. So H is a stabilizer, and this is a stabilizer Lie algebra. And so because P is arbitrary, these may not be reflected. Okay, so this is the setup, and we want to have this model. Okay, so let's first of all let's quickly recall what happened in the Lunar case. Okay, so the Lunar slice was essentially dictated by this. In the Lunar case, P was stable, so there was a reductive stabilizer, and it gave rise to this normal H complement, slice n, right? And then everything else was synthetic, right? Then you had these commuting actions and so on and so forth. Okay, so this is what we did. But of course, now we are at an arbitrary point P, so the orbit is not closed, and the stabilizer may not be reductive, and a normal H complement may not exist. Okay, so all we do initially is that we just replace n by v. Okay, so if you look at this whole vector space V, it is of course H module because it's a G module. G acts on V, so H also acts on V. Okay, so we just do the entire associated construction with n replaced by V. That is all that I'm doing. Okay, so I just everywhere where there was a capital N, I replaced it by V. So essentially you have this orbit and you put a slice of V at every point, if you like, right? So just a twisting of V along the orbit. Okay, the orbit may not be closed, but the twisting. So all these are still well defined. Okay, and what we get at the end is essentially this, right? So in the Lunar case, we had this normal size, and we had this map from the associated construction for n to the ambient space. Right now, n we have decided to replace n by v. Right, so we have this G equivariant map from GXH V to V. Right, and of course, just by dimensionality reasons, this map cannot be expected to be a diffeomorphism. Right. Yeah. Right, because it's just right. So what we do is that we essentially want to do a quotienting of this map. Okay, so we want to construct a Lie algebra quotient of this map. Okay, so yeah, so we have the G actions here. So we look at the induced Lie algebra actions on these two spaces, and we have this sort of G equivariant map at the group level, and it of course gives a Lie algebra equivariant map. At the Lie algebra level. Okay, so we have the Lie algebra setup. So we have, so let me kind of try to explain it like this. Okay, so this is the Lie algebra quotient. Okay, so we have the space X. Okay, so so when I apply it, my X is going to be this associated construction over full V. Okay, and my Y is going to be V. Okay, so that's the picture to keep in mind. And my phi is the F in this picture. Okay, so I have this space X, I have this space Y. Right, and I have this phi map, which I'm calling F here, right? And this map, so this is a sort of, there's a Lie algebra action here, there's a Lie algebra action here. This map is sort of an equivariant map for the Lie algebra action. And let's suppose that if I look at if I look at the fibers of this map, right? If I look at the point and look at all the points which map to this point, right? Suppose all these fibers are of the right dimension, right? The dimension being the dimension of the fiber being dimension of X minus dimension of Y, and this map F is kind of surjective. Okay, if that happens, then I can take a manifold, a submanifold of X, which is transverse to these fibers. Okay, and then I can actually produce a Lie algebra action on this submanifold. Okay, that's really the quotient construction. Just like you have a subspace which is stable, and if I give you a complement to the subspace, I can produce an action on the subspace, right? So just like the quotient construction for vector spaces, we have this quotient construction for Lie algebra actions on manifolds. Okay, it's quite Okay, so this is what we do, right? So given so and the action should be sort of thought of as follows: that given a point, right? So now given a point on this M, right? And given this group element, infinitesimal group element or the Lie algebra element, I would like to know which vector field on M, right, that this element will produce, right? And the way you do it is that when you look at which vector it will produce on the big X, right? And that vector you kind of decompose into a kernel component, right? Essentially along the fiber and transverse to the fiber. Okay, so along M and then along the fiber. Okay, and then you look at the component along M, and it turns out that this is actually a valid Lie algebra action on M. Okay, so there is this sort of very nice generic quotient construction, and this is what we would like to apply to this setting. Okay, provided, right, we have these nice properties. All fibers, at least in a neighborhood of the point of interest, are of the same dimension, right? And one is able to choose a transverse. Okay, and that's exactly what we do. Okay, so we need to choose this submanifold, okay, which is transverse to the kernel of this map P. Okay, because those fibers are going to get mapped to the same point, right? The kernel is going to be the distribution on the on this fiber. Okay, so this is what we need to do. We need to choose a submanifold which is transposed to the kernel of P, and here is a way to construct such a such a submanifold near the near the point of interest, this E comma 0. Okay, so what we do is that there are some choices to be made. So of course, so yeah, unlike the Lunar model, there are some sort of choices, inherent into this local model. So first of all, you have the group G, right, and you have the stabilizer subgroup, right. You pick a submanifold which is transverse to this subgroup. Okay, so pick a submanifold, at the identity point, which is transverse to H, right? So at the tangent space level, the two tangent space sort of complement each other. And then you pick any vector subspace complement to the orbit in the ambient space. Okay, so note that this slice or this complement may not be H invariant. Okay, and then one can show that this M cross N, restricted to a small neighborhood of E comma 0, essentially is sitting inside this associated construction. Okay, so there is a submanifold which is of the form M cross N, right, restricted to a neighborhood which is transverse to the kernel of this, and yeah, that is what we work with. Okay, so you fix the choices of M and N, and then what you show is that yeah, there are plenty of choices for M and N, such that this mu, this kind of this embedding is possible. Okay, so this local model is possible. So I will skip these calculations, but yeah, so this is really the point. Okay, so we have this map which is G equivariant and which is regular at E comma 0. So all fibers near A0 are kind of yeah, near A0 it is well behaved, and therefore by that abstract the algebra quotient theorem, once I have a transversal to the kernel of this map, I will get G action on that on such a transverse. Okay, and this M cross N for the choices of M and N produces such a. Okay, so what this sort of argument shows is existence and construction of the local model, right? But what is not sort of it says that there is this abstract sort of construction, but it doesn't explicitly gives the explicit Lie algebra action on this product structure M cross N. Okay, so this is something that will be described in the main talk, which will be given by Sonia on Thursday. Okay, so what I have showed is that there is sort of existence of the local model has been shown, but the explicit description of the action is extremely important, right? Because that's what makes many of these calculations possible. Okay, so that will be described later. Okay, so just to summarize, so we have this Lunar type model which applies to all points. It's local and at the Lie algebra level. And yeah, I have not given the explicit description of the Lie algebra action, so that will be covered in the next talk. And yeah, so we have used this local model to sort of understand the projective orbit closures for the conjugation action. Okay, and yeah, this is really the preview for the next talk. Yeah. Okay, so I think I'm done.